Today now we are going to see about the experiment of power system laboratory 2 for ME power system engineering students. This is experiment number 1, AC to DC power flow analysis. So the aim of the experiment is to perform AC to DC power flow analysis. So this can be done by two methods. One is sequential approach and then other one is simultaneous approach. So either any method we can use. So the software needed for this, we need to write a MATLAB program to perform this analysis. So MATLAB 2014 or any updated version we need. Then theory of this experiment is high voltage. We know about the HVDC technology. So there is a converter station which may be a rectifier. It rectifies AC to DC, and then in between after the converter section station there will be a DC line, HVDC line. HVDC line, we know the different types: homopolar, bipolar, like monopolar, like that. So DC link will be there. After that the converter station 2, that is nothing but the inverters, and at last we are giving to the AC system. So the combination of converter station 1, DC link, and then converter station 2, this is called as HVDC system. So these are the equations governing for the rectifier, inverter side, and then HVDC link. So the direct current flows from rectifier to inverter, that is ID is equal to VDR. VDR is the output DC voltage of converter station 1 and VDA is the input voltage to the converter station 2. So here R, suffix R represents rectifier and suffix I represents inverter, and V represents voltage, D represents DC voltage. Okay, so VDR minus VDC divided by RDC. So VDR, VDA are the DC voltage at rectifier inverted terminal respectively, and they are calculated. These are the formulas used to calculate. So VDR is VDR into cos alpha. Alpha is the firing angle of the rectifier, minus BR into 3XCR divided by pi into ID. So below I have explained what are the terms, what is BR, what is XCR, like that. So similarly, you will get all these equations. So here IDR represents the current margin between rectifier and inverter. That values you need to set for 10%. Then ETA is a converter transformer secondary voltage at rectifier and inverter respectively. B is the quantity, number of 6 pulse bridges at any side. So usually for a 12 pulse converter, there will be two number of 6 pulse. So the value of B will be 2, both for inverter and rectifier. So usually the HVDC link will be LCCC. Line commutative converter. So we will use a 12 pulse converter. So in the 12 pulse converter we will employ, for better performance, we will employ two number of 6 pulse converters. So the value of B will be, usually it will be 2. And XR is the leakage reactance or commutation reactance of the transformer we are using in the from the AC supply. You are using transformer. So that reactance is XC, and alpha is the firing angle of the rectifier, and gamma is the extension angle of the inverter, and beta is the firing angle of the inverter. So RDC is the equal resistance of the DC line. So I have already told the approaches to include HVDC link will be simultaneous approach and sequential approach. So simultaneous approach you can use by Newton-Raphson method for load flow analysis. Here we need to find elements of Jacobian matrix. So usually what will be the elements of Jacobian matrix, you have already done in your UG course, power system analysis. So in that we have already done the Newton-Raphson method. So you will have the Jacobian matrix J1, J2, J3, J4 into delta theta, delta V, that will be equal to delta P and delta Q. So like this you will get, this is called AC load flow. So you will get the value of real power and reactive power by Newton-Raphson method. So here you are incorporating a DC link in between any two buses. In between any two buses, you are incorporating the HVDC link, and then you are running the power flow, Newton-Raphson method. So that is one of the approach, that is called simultaneous approach. Another method is sequential approach. Here this is the flowchart for sequential approach. So sequential approach, you are taking the sending end bus, the net power flowing in the sending end bus is the real power in opposite side, minus P plus PDR, and similarly Q net is minus Q plus QDR. And for receiving end bus, P net is minus P plus PDI and Q net is minus Q plus QDI, where P and Q is the real and reactive power injected in the bus, sending end bus and then receiving end bus, coming out from the sending end bus and injected in the receiving end bus. So with this you can find the values of real power and reactive power. So initially you need, so structure of this sequential method is, initially you need to take a guess, then solve the DC system and calculate PDR, QDR, PDI, QDI, then solve the AC load flow and then update. Then you need to check for the convergence. If it is converged, then you need to repeat the procedure. If it is not converged, you need to repeat the procedure. You need to go again solve the DC system, calculate PDR, QDR, PDA, QDA, and then you need to repeat this process. So if it is converged, you can stop the solution. So this is what you can do for the AC load flow and DC, that is AC to DC load flow analysis. So in the previous years you have studied about DC load flow analysis separately, AC load flow analysis separately. Here by using HVDC link you need to do AC to DC load flow analysis. Okay, so this is one of the method. Here the sequential method is you can able to develop the MATLAB program for that. Thank you.